Okay, let's try sample problem 15.8. We're going to look at a real solving a chemical equilibrium type problem. This is a type that is, it's quite a few steps, but the algebra in solving this one isn't so bad. So let's take a look at this one. What we have is the equation, the balanced equation is given. So it's hydrogen gas plus iodine gas. So it's a pretty simple equation. Okay, everything's gas phase. And they tell us that the value of Kc, the equilibrium constant, is 54.3. Okay? And then they tell us the initial concentrations we start with. So I'm going to put I. The initial concentrations are 0.240 molar, 0.240 molar, and they don't say anything about HI, so we're going to assume that's 0. If they don't say what this concentration is, it probably is 0. Okay, so what do we do here? It says, what will the concentrations be once we reach equilibrium? What will the concentrations be at equilibrium if we start with 0.240 molar concentrations of both HI and I2, H2 and I2, sorry. Okay, so this is going to be one of those initial change equilibrium problems. So here's what we're going to do. First step, calculate Q. Remember, Q is the concentrations of the products divided by the concentrations of the reactants. Okay? And these are the initial, so I'll put a little 0 there. Okay? Don't forget that whatever the coefficients are in front of the reactants or products, those become the exponents in the equilibrium constant. Okay, so the initial concentrations, HI is 0, divided by 0.240, 240. Now, get used to doing little algebra tricks. 0 squared, right? 0.240 times 0.240 is 0.240 squared, right? Those numbers multiplied together are the same number, so it's squared. Now, what's this equal to? Is this equal to infinity, or is it equal to 0? Okay, if it's 0 divided by a number, that's equal to 0. Okay? So QC is equal to 0. Now we go back to the guidelines. The guidelines were if Q is equal to K, you're at equilibrium, nothing will happen. If Q is greater than K, then that means you have too much products and it'll go back to the left. If Q is less than K, that means you don't have enough products and it'll go to the right. So the idea here is that in order to get to an equilibrium constant that is larger than 0 and up to 54.3, the way that you go from 0 to 54.3 is the numerator has to go up and the denominators have to go down, right? If this number at the top gets bigger, that's going to make it larger than 0. So we want to get it up to 54.3. So that means this has to increase, so that means the reaction has to go to the product side. So now we say, okay, it's got to go to the product side, so plus 2x. Remember, that exponent or that coefficient gets brought down here. And then these have to go down. Whatever happens to the right side, the opposite happens to the left side. They can't all go up or all go down in this type of problem. So if you've decided based on the fact that Q is less than K, so the reaction's got to go that way, that means you're going to get the plus x's on that side and the minus x's on that side. If you decide, hey, QC is greater than K, well, then it's going to go the opposite direction, and you'll get the plus x on the left, and you'll get the minus x on the right. Okay? Let me erase some of this. Now the next step is to take a look at completing this ice table. Okay? We figured out the initial concentrations because those are given. we've now figured out what the change is going to be based on the stoichiometry. The reason it's minus x, and plus 2x, that's 1, 1, and 2, are these coefficients here, 1, 1, and 2. Okay? So now, for the equilibrium, you just take the change plus the initial. So initial plus change. So 0.240 plus a negative x. So that's minus x. 0.240 plus a negative x. Now notice I took the concentration units of molarity out just so that it's a little bit simpler looking in the table. And then 0 plus 2x, well, that's just 2x. Okay? These are equilibrium concentrations. So we can plug them back into 54.3. 54.3 is going to be equal to the concentration of HI at equilibrium squared, don't forget those coefficients, divided by the concentration of H2 at equilibrium, divided by the concentration of I2 at equilibrium. So that would be, here's our terms. These are algebraic terms, but they're just like numbers. 2x squared, right? It's HI, and HI is 2x, so it's HI squared, so it's 2x squared. Now, here's the little trick that I did a little bit earlier, 0.240 times 0.240. If I have 0.240 minus x times 0.240 minus x, how can we simplify that? If I had 2 times 2, that's 2 squared, right? So I'll do the same thing in the denominator here. This is 2x squared over 0.240 minus x squared. Be careful when you do these problems. There's a tendency, if you're really experienced in algebra, to want to express that 2x squared in the numerator as 4x squared, right? You actually might want to do that. Hold off from doing that until you see what you have to do. So this is k. Now, here's the thing. This is equal to 54.3. So this is a specific type of problem where you have something in the numerator. So let me write it this way. You got a number, 54.3, and it's equal to something squared divided by something squared. If you have something squared divided by something squared, you can take the square root of that to simplify it. So we have to take the square root of this one side. So this is the simplest type of algebraic problem of this type of problem, where you have something squared over something squared. So you can just take the square root of both sides. So what I'm going to do, let me erase this. I'm just going to take the square root of everything. The left, the middle, and the right. And the square root of 54.3, I don't know what that is, but I do know the square root of 64 is 8, and the square root of 49 is 7, so we know it's between 7 and 8. It's going to be 7 point something. So square root of 54.3 is 7.369. Okay? So that is going to be equal to the square root of kc. That is going to be equal to 2x over 0.240 minus x. I got rid of the square in that intermediate term there. Okay? And don't mess with me over whether this is plus or minus. In fact, you're right. There's two answers to this. It's plus 7.369 and it's minus 7.369. We're going to ignore the negative root of this and just worry about the positive root. Okay? Now, what we have here, I'm going to box this off because I'm running out of room on my screen, is we now have a way to easily find x. We've made it to a point where we can find x. There's no x squared in there, so we don't have to go through any complicated algebra. We're just going to solve for x here. So let me get rid of this over here. And we're going to work with this over here. Okay? If you have a over b equals 2, let's say, and you want to find out what a is, you would just multiply both sides by b, right? And that would let you find what a is. We're trying to figure out what x is. So our first step algebraically to move with this is to multiply the denominator by this number and set that equal to the numerator. Okay, so I'm going to do that. 2x is the numerator, is going to be equal to 7.369 times 0.240 minus x. I'm going to keep that in parentheses because we're multiplying the entire denominator by 7.369. Now we do what they call distributing. You take the number in the front here and you multiply it by that, and then you subtract that number times the x. So 2x is going to be equal to 7.369 times 0.24. Well, let me go ahead and solve that, or go ahead and calculate it as soon as I get my calculator on. Oops. Sorry about that. Here's one issue, which is that my calculator just died. Sometimes these solar calculators don't work very well in the room. Okay, so 7.369 times 0.24 is 1.769. And then we're going to take the 7.369 and multiply it by minus x. So minus 7.369x. Okay? Now we're at the next algebraic step, which is we want to combine like terms. So we want to combine these two terms here. So since you could do it either way. You could try to get the x on the right side, or you could try to get the x on the left side. I'm going to try to get it on the left side because I've already got the number over here. So I'm going to try to move this one over to that side. So the way you would do that is you would add the opposite sign. This is minus, so add the positive sign to both sides. That way these add up to 0. So I have to add 7.369x to the left side. And that would give me 1.769. Okay? Now these are like terms, so you just add the coefficients, right? 7.369x plus 2x is 9.369x. And that would be equal to 1.769. Now to solve for x, you divide both sides by this coefficient, 9.369. Okay? So if you take 1.769 and you divide that by 9.369, you get 0.1888 or 0.189. So there's our x. Now often students, when they do these problems, will just stop right there. Hey, I found x, I did it. This is not a math class, so this is a chemistry class. Let's go back to the original question. What will the concentrations be at equilibrium if we start with 0.240 molar concentrations? In other words, what are these numbers going to be? What is 2x going to be, which is HI? What is 0.240 minus x, which is I2? What is 0.240 minus x, which is H2? Okay, we want to find those concentrations. So let me work over here. We figured out what x is. So the concentration of H2 at equilibrium, by the way, is equal to the same as I2. They're the same. They're exactly the same. So that's equal to the concentration of I2 at equilibrium. And that would be equal to 0.240 minus 0.189. Okay, so 0.240, that'd be what? 0.051. Let me check that. 0.240 minus 0.189, 0.051. Molar, right? These are concentrations. So there's two of the answers right there. The final concentration, the equilibrium concentration of H2 and I2 are 0.051. But what about HI? Concentration of HI at equilibrium is 2x. 0 plus 2x, right? So that would be 2 times 0.189 molar. So 2 times 0.189, 0.378. Probably too many sig figs there, but that's okay. Well, it said there's 3 there, so I guess that's okay. So there are our equilibrium concentrations. Now, think about all the work we did there. And believe me, there's harder ones than this one. But the work we did right there, how do we know these answers are right? These could be completely off. How do you estimate? Well, here's what you do. You come back and you say, well, we're not sure whether these are right. Let's check them. So you come back and you calculate QC. QC is the concentration of HI squared. So let's say that we don't know whether this is equilibrium. So we'll put 0.378 and square that. And then we'll put in the concentration of H2, which is 0.051. And the concentration of I2, which is 0.051. But wait a minute, they're the same, so just make it squared. And let's see what we get. If we get a value that's close to 54.3, that means that we pretty much got it right. So 0.378 squared divided by 0.051 squared comes out to 54.9. Okay? Pretty darn close to 54.3. If we did it to 2 sig figs, we'd actually have exactly the same answer. Okay? So it looks like we got it. This is a check for this type of problem. You plug your final concentrations, your equilibrium concentrations that you got, back into the expression for Q, and if Q is equal to K, we're at equilibrium. We got it. So there you go. All right. So you may need to watch this video a couple times to go through the algebra, but essentially this is how we would go about it. Now I'm going to show you another example from your textbook in a different video where it gets a little bit more complicated than this, and we have to use a different type of algebraic technique. But if you have a situation where you have something squared, the numerator squared, divided by the denominator squared, you can use this approach where you take the square root of both sides. So the square root of k will then tell you how to proceed, and you can use this algebraic approach. Okay? Good luck.